Well, good morning. This is it's already 8:09. I've been sitting here trying to get PowerPoint to open, Screencast-O-Matic to open, and then when it did open, I found out the file that said it loaded last night was nowhere to be seen. So I had to, in fact, it didn't even take its correct name. So I had to redo it from scratch today. So that's why I'm a little late getting started. But we're starting now, and unfortunately I'm the only one in the classroom. So I hope some students will be coming in. I know the weather's rainy, but it's not that bad. But hopefully some people will be coming in. Waiting now, it's just like everything this morning is taking forever. Here we finally have our screen. I did want to let you know a couple of things. I think maybe I announced this last time, but just in case you missed it. I did get everything, as far as I know, uploaded on Blackboard. The syllabus is there. The locator card is there. I'll come back to that. The research paper instructions there. All the YouTube videos and other resources that students that I've either found or students have sent me, I've loaded those. And then, of course, there are no PowerPoints because this book doesn't supply any. But I have loaded the link to this class's YouTube videos. So that's all out there under content and Blackboard. Now, waiver, caveat, whatever you want to call it. Unfortunately, I found out after I had done all that they may be paying me for an overload. Well, if they pay me for overload, I have to extend my office hours because you're supposed to work extra hours if you're doing an overload. So I went through and changed the syllabus last night and changed the locator card, but I don't have those loaded on Blackboard yet. I hope that this afternoon, or this morning or afternoon, I will be able to get those loaded onto Blackboard. The others removed and these loaded. Now, let's see. In addition to that, or with that, we might go with something else. It's on the coop, so if it is, I can't recall what else. Okay, we're on, still in Chapter 1, Section 1.1, but we should finish this soon, very soon. Top of page 10. Since nobody's here, I'll probably read more than I would because I don't know if you have books or not. Sometimes a differential equation possesses a solution that is not a member of the family of solutions of the equation. That is, a solution that cannot be obtained specializing any of the parameters of the family of solutions. Such an extra solution is called a singular solution. Now, earlier we talked about a particular solution, which I think meets all the same requirements of a, well, no, I guess not. I guess a particular solution would be, it seems like to me they're pretty similar, okay? But this is a singular solution. For instance, we have seen that y is equal to 1/16 x to the fourth and y is equal to 0 are solutions to the differential equation dy dx is equal to x to the minus 1/2. Now this is one we had done earlier. I'll write it down again. Y equal 1/16 x to the fourth, I believe it is, right? And y is equal to 0, are both of these are solutions for this differential equation. Dy dx is equal to x y to the 1/2. Okay? Now, and this is on the interval minus infinity to infinity. Everywhere, those are solutions. Okay. Now, coming up in the next chapter, not just that section, next chapter, 2.2, we'll demonstrate that by actually solving it, the differential equation possesses the one parameter family of solutions, which the first of those is a part of. But notice that the trivial solution is not part of that. So here is that family of solutions that this is a part of. Y is equal to 1/4 x squared plus c squared. Okay? And certainly if you have c equals 0, square 1/4 x squared, you get 1/16 x to the 4th. However, there's no way that you can, as a general solution, y is equal to 0. Okay? Even though we know it is a solution. Okay? Now, by the way, this is only good for c greater than or equal to 0. Okay? I didn't put that down. Now, when c is equal to 0, the resulting is that y that we had to begin with. But notice a trivial solution is a singular solution since it is not a member of this family of solutions. Okay? There is no way of assigning a value to a constant c in order to obtain y is equal to 0. In all the preceding examples, we use x and y to denote independent and dependent variables respectively, usually x being independent, y being dependent. But you should become accustomed to seeing and working with other symbols to denote these variables. For example, you could denote the independent variable as t, dependent variable as x. In physics, you see that all the time when you're talking about motion. You know, your displacement, your x, is dependent on the time. Your velocity is dependent on the time. Your acceleration is dependent on the time. So quite often you have that. All right, let's look at example 9, which they give here. So let me erase this and go to example 9. Here are some functions. The first of these is x is equal to c1 cosine 4t, and the other is x is equal to c2 sine of 4t. Okay, notice in both of these functions, x is dependent on independent t. T is the independent variable, x is dependent. Two-parameter family, so by the way, you haven't learned this yet, this will lead to a second-order differential equation. Okay? C1, C2 are arbitrary constants or parameters and are both solutions of the, and both of these are solutions for this differential equation. They claim x double prime plus 16x is equal to 0. Okay? Now notice nowhere in there t shows up, but the x double prime is second derivative of x with respect to t. Okay? Now, what we need to do is verify and make sure that these are solutions to that. So what do we got to do? We've got to first take a derivative. X prime is equal to, now, you know the C1 is going to be there. Derivative of cosine is a minus sine 4t, but then the chain rule says take the derivative of 4t, which is 4. So I'm going to pull it out front. Similarly over here, x prime is equal to, c2 is in there. Derivative of sine is cosine 4t, but then derivative of 4t is 4 again. So that's with a plus. Let's take a second derivative, because the first derivatives don't actually show up, but you have to take the first to get the second. So x double prime here is going to be the minus, and the C1 is still going to be there. I'm going to hold off on the 4 for a second. Derivative of sine is cosine 4t times 4. We already had a 4, so that makes it 16. Over here, x double prime is equal to, you know the C2 is there. Derivative of cosine is negative sine 4t times chain rule. Derivative of 4t is 4. Multiply that with the 4 you already had there, and there's a 16. So, what we want to see is if indeed this equation is true. Let's plug in the first one. Minus 16 C1 cosine 4t plus 16, and your x is C1, oops, that's ugly, cosine 4t, and sure enough, that obviously is equal to 0 no matter what C1 you put in there. Over here, if you plug the second one in, you get minus 16 C2 or sine of 4t, and then you plug in a plus 16 times this x, which is C2 sine of 4t, and sure enough, that is identically equal to 0. Okay, no matter what C2 you put in there, that's always equal to 0. So indeed, these two are solutions to that differential equation. Okay. So what is your solution? These are certainly solutions. Can we generalize them? What is your, and you could call this x sub 1 and x sub 2 if you wanted to, your overall x then is equal to, and this is what they have is called the superposition principle, or linear combinations, which I'm not sure we've hit yet, but we will. Your overall solution is C1 cosine 4t plus C2 sine 4t. Okay? It's a combination of those two with arbitrary constants C1 and C2. Now, you might ask yourself, well, are there other solutions out there? Well, you can rest assured that since this is a second order differential equation, two parameter family is all you need. So anything else that you find out there will be a particular or a singular solution. This one has none. Okay? All right. Now, let's move to another one. And this is somewhat of a stranger set of circumstances. Here's what we've got. You've got a family of solutions, and here's what they are. Y is equal to cx to the fourth. Okay? Now, we know, or they're telling us, that is an explicit solution to xy prime minus 4y is equal to 0. Again, one parameter here, we didn't have to put C1, C2, because this is a first order differential equation. Again, we haven't actually done that yet. I'm just telling you that's a fact. I mean, that's something you'll see later. Okay? Well, let's see if this is indeed true. What we've got to do is figure out what y prime is. Y prime is equal to 4cx cubed, right? Let's plug that into our equation. X times 4cx cubed minus 4 times y, which is cx to the fourth. What is that equal to? Well, this is 4cx fourth minus 4cx fourth. Indeed, that is identically equal to 0. So yes, that is a solution. Okay? Now, it says it's a solution on the interval minus infinity to infinity. Okay? Everything's looking good. They said verify, we just did. Now, they, in the book, and I'm not going to draw this for you, so if you don't have the book, get you a book, get you a e-book, rent a book, find it, I don't know if it's in the library, see if you can find it somewhere to view this, and you'll see this figure 1.1.5a shows two explicit solutions here. Okay? One of these is with c equal to 1, that solution equal to 1, y is equal to x to the fourth. And in your book, in fact, I guess I will go on and try to draw it. If you recall how this looks, they drew one blue, so let me, well, let's see, before I do that. No. Okay. All right. Before I do that, let me just tick off a few points. 1, 2, 3, 5. We don't need all these. We'll never get there. And here, and there, 1, 2, 3. Never get here either, but I'm just going to do it. And 1, 2, 3, 4, 6, 7, 8. Okay, not going to get much of that either. And later we'll go down here. Okay. Now, when c is equal to 1, y is equal to x to the fourth, it'll be 0, 0, 1, 1, minus 1, 1. 2 to the fourth power is 16. Off scale like crazy. So this goes up very rapidly, comes down, flattens out pretty smoothly. And here's where I meant to change color. In the book, they make this the blue curve. I think it's sort of a light blue, so let me make that the blue curve here. Flattens out here around 0 and goes up sharply here. That's what when c is equal to 1. Okay? When c is equal to minus 1, though, this is their red curve, then you have minus x to the fourth. Well, that's going to be 0, 0, 1, minus 1, negative 1, minus 1, and on. So it's going to be a function, does the same type thing, flattens out pretty steep here, and then goes down pretty steeply there. That's what it looks like when c is equal to minus 1. Now, certainly if you let c equal 0, you have the function, so this is not a singular solution, you do have the function y is equal to 0. That would be on the just the x-axis. Okay? Go back to black, and this would be x, this is y. Okay, so x equals 0 would certainly just be the y is equal to 0 would be the x-axis. That's when c is equal to 0. Now, pick a, all right, the red and blue solution curves show that, and the graphs that, okay, correspond to the choices C1 and C2. The piecewise defined differential function, okay, is that here's another one. They're just making up one here. Here's another function. Y is equal to this part, I'm sorry. Let's make it minus x to the fourth when x is less than, and do they put equal there? No, they just put less than 0. And positive x to the fourth when x is greater than. You really should include or equal to in one of the others of them. Guess what? That's a piecewise defined function that basically covers the left-hand wing of this one and the right-hand wing of that one. That piecewise defined function is also a solution, okay? And you would use this part here, go back to blue, again when c is equal to 1, but also x greater than, and this time they do put the equal sign 0. They didn't there, I think you should. And the part down here is c is equal to minus 1 and x is less than 0. That would be this thing. So forget about this one over here and that one over there. Let's combine those two. It's continuous. It's smooth. It's also a solution, a piecewise defined function. cannot be obtained from y is equal to c x to the fourth by a single choice of c, so you have to have, for piecewise defined functions, even if they're smooth and continuous, you might need different c's. The solution is constructed by choosing a c equal -1 for one part and c equal +1 for the other part. I'm not really sure why they told you that, except that is a legitimate solution. Now let's look at some systems of differential equations. We're not going to do too much with that, but let's just take a glance. Up to this point, we've seen discussing single differential equations containing one unknown function, but often in theory, as well as in many applications, we must deal with systems of differential equations. A system of ordinary differential equations is two or more equations involving the derivative of two or more unknown functions of a single variable. Okay? Now catch that. Single independent variable. Okay? If you think about systems of linear equations, which you've done in earlier math courses, generally you're going to have, if you have two equations, you have two unknowns, and they're both independent. Three equations will take at least three unknowns, all three independent. Okay? Not here. You have one independent equation, one independent variable, and then you have others dependent variables. Okay? X and Y denote the dependent variables. By the way, for example, X and Y denote dependent variables and T is the independent variable. Then a system of two first-order differential equations will be given by something like this. Let me go to a clean screen now. I'm not really sure why they bring this up here, except just to say they brought it up, but here's what it is. Let me get my pen back. Okay. dx dt, that's the first of the independent dependent variables as a function, derivative of that as a function of the independent variable, is some function that's a function of t, x, and y. Okay? Where t is the independent variable and x and y are dependent. And then dy dt would be some other function, g, of t, x, and y. So you see there, of the same three variables, a solution of such a system as this is a pair of differential functions, a pair of differentiable functions. X is equal to phi of t, and y is equal to, well, let's call it phi 1 of t, and y is equal to phi 2 of t. Okay? Defined on the common interval I. All this is on some interval I. Okay? And these two functions must be defined on that. And each of these must satisfy both differential equations. Okay? The first one satisfies the first one, the second one satisfies the second one. Well, no, I mean, they both satisfy each other. Okay. Now, this book has these remarks at the end of every sections, and sometimes they're good and instructive, and other times they just seem to muddy the water miserably. Here's one that has potential for muddying. It might not be apparent whether a first-order ordinary differential equation written in differential form, that's m of xy dx plus n of xy dy, is linear or nonlinear, because there's nothing in that form to tell us which symbol denotes the dependent variable. Okay? So just a little comment there, they don't do a thing with. The second little remark is we'll see in the chapters that follow that a solution of a differential equation may involve an integral defined function. And one way of defining function, capital F, of a single variable x is by means of an integral, a definite integral. And it sort of goes back to first fundamental theorem of calculus part 1. And if that integrand, and I'll write it down here for you, guess I'll go on and clear this. Okay. Here is your integral defined function. Capital F of x might be some integral from some value a to the variable x of g of t dt. Okay. Now, before you panic, I hope that you've run into this before, that t in the integral is just a dummy variable. You can name it anything in the world. You're integrating it out. Your answer is going to have whatever the antiderivative of g is. You're going to plug in an x. That'll give you a function of x. You'll plug in the a. That's going to give you a constant. Okay? So, the t integrates away. So you can put anything there. Stickman. Anything you wanted to. Okay. But that gives you just a function of x. Constant doesn't count. Okay. Now, what they're saying, if that integrand g is continuous on the interval a to b, where x is somewhere in between a and b, then the derivative form of the fundamental theorem of calculus states that f prime of x, okay, I hope you remember this. When you take a derivative of an integral, they undo each other. Those are inverse operations. They're not inverse functions. They're not functions, but they're operations. Inverse functions of each other. Operations of each other. And that will just give you and you could write it out, they write it out in the book, d by dx, because that's your independent variable here, of the integral a to x g of t dt. Okay, that's what you're doing, taking derivative of it. And by this, the derivative undoes the integral undoes that, and that leaves you simply g of x. Okay, now that first integral up there is often non-elementary, because if you had an elementary function, the odds are you're going to get a solution. Okay, so sometimes these are non-elementary. In fact, quite often the integral of the function g does not have an elementary function antiderivative. In other words, you wouldn't have been able to do the antiderivative anyway. Okay, so the elementary functions that include the familiar functions studied in typical pre-calculus course will be the constant function, okay, any polynomial function. These are all elementary functions. Okay, rational functions. Okay, and rational functions, remember, have limited domain sometime if there's vertical asymptotes, which there could easily be. Okay, but other than that, they're elementary. Exponential functions, generally no limit to the domains of those. Logarithmic functions, again, remember, logs are only defined for the independent variable greater than 0. Never negative, never 0. Always greater than 0. But they're still there. Your trigonometric functions, remember, sines and cosines are defined everywhere, but all the rest of them have some limitations on the domain, but everywhere in the domain they are elementary functions. Okay? And then also your inverse trig functions. Okay? Now those are much more restrictive, because remember, for a trig function to have an inverse, it must be 1 to 1, and every trig function repeats itself indefinitely because they're periodic functions. So therefore you have to restrict yourself to one period, and you have to make that a period that is a 1-to-1 period. Okay, that is that doesn't repeat itself, either strictly increasing or strictly decreasing, and that's the only place where the inverse trig functions are defined. That's their domain, the only place where the inverse functions are defined in a domain, so therefore that's the only place they're elementary, but they are elementary there. Okay, and then you can do powers of any of these functions, and that's rational powers. Okay, raised to some number or raised to some fractional number, which means the rational number means the numerator is what power you're raising it to, the denominator is the index of the radical that you're taking a derivative of. Okay, now, and those have some limitations, which I'm sure you're aware. If you're taking an even root of a function, that can never be negative. You have to restrict your variable so what's under the radical of an even root function is never negative. Can be zero, but never negative. Okay. Then you also have finite combinations of these functions using addition, subtraction, multiplication, and division, as long as you don't divide by zero, and function compositions of these functions. So all these would be what we call elementary functions. Okay? They give some really bizarre ones, like this, e to the minus t squared. That's your exponential function, multiplied by a radical function. That would be a see, where did they mention? They didn't mention this, but certainly it is true. The square root of 1 plus t cubed, okay, cosine t squared. There is a composite function, okay? So those are all rational powers of the thing. This is a rational power of a polynomial function. That's what makes it okay. Okay. These are all elementary functions, but some of these elementary functions, good luck with integrating. Okay. For instance, the integral of e to the minus t squared dt. Good luck with that one. There's no way to integrate that except numerically. Okay? But you can just leave it in that form, and then you can take derivatives and other things. The integral of and I'm sorry, this was supposed to have a comma in between it because they're doing each of these separately. The integral of that one, the square root of 1 plus t cubed dt. Try integrating that one. Don't think it's going to happen. Okay? And the integral of cosine t squared, same deal. No way you can do that. No method whatsoever you can do it. But you can leave those as answers. Okay? All right. Number 3, I don't know if that's worth going over or not. Goodness gracious. Number 4, a few last words about implicit solutions. Differential equations are in order. I think we already hit most of that, so I'm going to skip that one. Might not seem like a big deal to assume that that can be solved. Remember the generic form, capital F of x, y, y prime, y double prime, all the way up to what the nth derivative of y equals 0. That can be solved for y to the nth derivative of y. But one should be a bit careful There are exceptions, certainly some problems connected with those assumptions, so I won't go in. All right. One more thing, general solution. I don't know if you remember, I was in search for the word and couldn't come up with it. When we had two single parameter solutions, we said we can combine those together, and I couldn't think of what you call it. That's the general solution. All right, homework exercises here. Do any of the odds 1 through 7. Hopefully you've already done that. 9, either 11 or 13 or both. Either 15 or 17 or both. Do 19, either 21 or 23 or both. 25 or 27 or both. 29, do 29, either 31 or 33 or both. Do 35, either 37 or 39 or both, and do 41. Think all those odd answers are in the back. The discussion problems you can look at, think through, work on. I don't think many of those answers are in the back. If you do find some of those, fine, go for it. But I wouldn't say don't look at them. Read through them, see if you understand what they're talking about, and occasionally light upon one like number 51, which is talking about the folia of Descartes. Excuse me, my throat's hurting. There's a couple of potential paper topics. Who was Descartes? How did he develop or come up with this folia of Descartes? What's it used for? What's applications of it? There could be several potential paper topics there. Okay? And then they have some computer lab assignments. If you have access to any of the computerized programs like SATCAS, Computer Algebra System, you can certainly do those as well. Okay, let's move on. Oh, and by the way, let me say this. I've taught this course out of this text, this edition of this text, 2, 3, 4 times. I don't remember how many. Not that many. I used to not test you on chapter 1 because that wasn't really in the course description, but it's all essential stuff to understand. So I combined 1 and 2. 2 is a very long chapter, so that got to be a long time passing. So decided either last term or term before to go back and test separately chapter 1 and then chapter 2. It gives you a test a little bit earlier. But ever since I've done that, it seems like people have really struggled with that first chapter, the first test. And this is just an introductory chapter. And it's kind of a mystery to me why the struggle's there, except, and I may be wrong on this, but it seems like to me the only reason I can think of that should be happening is they haven't done the homework exercises. These seem like maybe nebulous or stuff. If you don't do these, you're going to struggle, I think, on the first test. Now, unless you're really good at it and pick this up real quickly, I would say do these homework exercises, at least some of them, so you can move on and do well when that first test comes around, which is not that far away, by the way. So let's move on to 1.2. Going to be talking about something that's going to come up many times later. These are initial value problems. We're often interested in problems in which we seek a solution y of x on a differential equation so that y of x also satisfies some prescribed, what they call side conditions. You got a few conditions on the side here. Well, if you think back, everything we've done so far, or you may not realize it, but it has been, if you didn't have those prescribed, you wind up with a family of solutions. If it's the first order differential equations, you have a one-parameter system. Choose a different C, you get a different solution. Well, that's can cover a lot of space. And then when you have a second order polynomial differential equation, you're going to have 2 independent parameters. And you can choose any value for one, any value for the other, and you can get functions all over the place, some that don't look at all like the others, because they may curve up or curve down or loop one way or another way. Yeah, you get an infinite number of solutions. Well, in real life, usually you're looking for one solution. So usually in real life, you have to know some set prescribed side condition. That is, conditions that are imposed on the unknown function y of x and its derivatives at some number x0. Now the x0, now that's assuming that's your independent variable, y is your one and only dependent variable. Okay, with that assumption in place, we usually think of x sub 0 as being, well, if it was t sub 0, you think of that as a starting time. And that's why they usually call it an initial value problem. But it doesn't have to be starting, it's just some value. The sub 0 just means a fixed x as opposed to x, which is a variable x. So it has nothing really to do with initial, except it's some place to start from. Okay? You might go backwards or forward from there, but it's some place to start. So when you have the unknown function, but you don't know something about it at one particular value, x0, and each of its derivatives at that same x0, then you have what we call an initial value problem. Whether it's the first value or not, whether it's where you start or not, it's some value. So, okay. On some interval I containing x0, of course that x0 better be in the interval, okay, the problem of solving an nth order differential equation subject to n side conditions. So if you have an nth order, third order, that means y prime is in there and nothing any higher than that, then you have to have at least 3. If n is equal to 3, then you have to have 3 side conditions at the same point, x0. So here's an example. dny dx to the nth, okay, is equal to some, now, I think this is usually the conventional use. If we were just calling this capital F, then all of these would be in, including dy dn, the nth derivative of y with respect to n, with respect to x. But when you pull that out, then you make it little f. I think that's what we've done. So this is some function of x, of y prime, of dot, 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 up to and including the y to the n minus 1. That's the n minus first derivative of y, okay, with respect to x, okay? Now when you write it the other way, the nth derivative of y is included under the capital F, and then that's equal to 0. But when you solve for the maximum derivative, dny dx to the n, the nth derivative of y, then you're left with these, okay? But notice you still have n variables. 1, 2, 3, 4, 5, yeah. 1, 2, this would be 3, and when you count all the way up to n minus 1, actually you have n plus 1 variables because, let's just start here. 1, 2, 3, 4, up to n minus 1. Y would be n, and then x would be n plus 1. Okay. Now, what must these conditions be? Typically, they're this. Y at this value x0 is equal to some value y0. Now, again, the sub-0, that's just a marker. It's just a counter. It doesn't really mean anything. It doesn't mean original or initial or anything else, even though we call it initial value problem. It just means it's some fixed value. When x is equal to x0, the y function is equal to y0. Just some fixed value. Okay? Y prime at x0 is some fixed number, and we'll call that, they call it y1. Okay? Some other value, okay? And y double prime at x0 will be some other value for y2, let's call it, okay? And we'll keep going with that dot, 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 up to and including the n minus first derivative as a function of x, but evaluated at x0, that same point, that same value of x, this will be some y to n minus 1. Now, these tick marks here, those should indicate derivatives. These down here just indicate a marker saying that's the value that goes with that derivative, okay? That n minus 1 has no real physical meaning. The one up here, that indicates it's the n minus first derivative, okay? Where all these, y0, y1, y2, y sub n minus 1, and everything in between are arbitrary constants. Arbitrary. They could be anything. And this is called an nth order because your derivative is to the nth power. That is an n there. It looks a little like a 2. The nth order IVP, initial value problem, because you have n plus 1 initial values that you've taken into account. No, I'm sorry. N equation. Because you see the x is x0. That's not anything. That's your given, and then you have these other values. N minus 1 of those y's, plus your x0. So I guess it is n. Okay. N plus 1 actually. Okay. These are called the initial conditions. Okay. Initial value problem, those are your initial conditions. Every one of those. Okay. That's the equation here. One initial condition, one initial this and that. Each of those is an initial condition. Those are the arbitrary constants, but you have initial conditions. Okay, solving an nth order initial value problem, such as the top one there, frequently entails first finding an n parameter family of solutions of the differential equation, then using the initial conditions at x0 to determine n constants of the family. Okay? The resulting particular solution is defined on some interval I containing that number x of 0. So let's take a look. Again, this is going to be hard to do without drawing. Okay? I'll try to do this. Since I will have to draw, let me get to a clean page. So, let's start with this one. dy dx, so this is a first order differential equation, so this is just going to be some function of x and y, because this is the first derivative here, one less than that would just be the zeroth derivative, which is the function itself. Okay? Now, that requires one initial condition. First order, one initial condition. Okay? And that condition would be y at some value x0 is equal to some other value for y, y0. Again, the sub-0 is just a marker. It has nothing to do with the value of it or anything. It's just when x is equal to x0, y is equal to y0. It just says these belong together. Okay? There's your initial condition. Now let's just say that if you had done your solve that first order differential equation there, whatever it was, and got a family of solutions, and they did something like this. There's one, there's one, there's one, there's one, and there's one. Usually they don't cross. Just let my pen get a little away from me there. Let's see if I can get that to disappear. Let me get this to disappear too and just draw it better. Okay. Okay, something like that. If every one of those is a solution for some different C, okay, you got a solution with so many C's here, arbitrary constants. But when you plug in x0 and you get a value that's right here, this doesn't have that value, this doesn't, that doesn't. That's the only one that does. This then, ding, 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 that's the winner. That's your one and only solution you're interested in. The others, yeah, they go for other values, but at x equals 0, that's not equal to y is equal to 0. Okay? Now, that's pretty cut and dried for a single first order differential equation. Okay? Now let's go to the next possibility for a second order differential equation. Okay? Then you have a d2y dx squared, and that's equal to some function of x, y's, and y primes. Okay? Because you always go to one less than what the original was. So you're going to need two initial conditions. The first will usually be just like the other, y of x0, some value is equal to y0, some particular value. Okay? But then you also need to specify y prime at that same value, and that's going to give you, say, a y1. And again, the subscripts just mean it doesn't have to be the same as y0, it can be some other y, but you're evaluating the first derivative at the same value x that you did before. Okay? Now, let's say that here are your solutions. I'll keep them in the first quadrant like they do in the book. Okay? Let's say you have a solution here, a solution there, a solution there, a solution there, a solution there. They don't have to be parallel or anything else, but they just typically do not cross. Okay? Now, and this is the interval of concern, I. You don't care what's going on outside of that. You just have to have this being defined in there. Okay? I think that one already is. Okay. It may not be enough to say that at x0, this is y0. Okay? That may not be enough. Okay? Because this function, but you also have that the slope here at that value, which is what the first derivative tells, your m here is equal to y1. Okay? That's what it tells you. You must match up not just the point, but also the first derivative. Now, to me, this illustration doesn't show that well enough. Okay? But that's what you're getting at. You've got a fixed value there and a fixed slope there. So if you had had other things there, say that or something, then that may not, it has the same value there, x0, y0, but the slopes may be very different there. Okay? So therefore, you have to pick the one curve that has that same slope, as well as the same value. Okay, those are your initial conditions. Okay, and we do that in physics all the time. You have, and they talk about here the word initial conditions. If you have some initial time t0, then your y there is going to be y0, your y prime there will be y1. Those will be derivatives there. Okay, so let's do example 1. Enough talking about it, let's actually do it. Okay. Okay. Just trying to keep up with where I am, what we're doing. Example 1. if you go back to problem 45, I don't know if you did it or not, probably not yet, hopefully you will do it. Exercise 1.1, you were asked to deduce that y is equal to c e to the x okay, is a one-parameter family of solutions of the simple first-order differential equation y prime is equal to y. Okay? All the solutions in that family are defined on the interval minus infinity to infinity. Exponentials defined everywhere. Okay? So, let's first verify and see if that's right. Let's do y prime, and that's going to be c e to the x, and sure enough, c e to the x, that's y prime, is equal to c e to the x. That's your y. Sure enough, that's true everywhere. Everywhere on that interval. Okay? So we know that. So, pick a different c, you have a different function. Okay? I'm not going to plot all those, but they do in the book. I will, I guess, plot a few of them. I can't plot them all because there's an infinite number. Okay, when c is equal to, they don't usually do this, but when c is equal to 0, that function is just y is equal to 0. Okay, and that would be your x-axis. Okay, trivial kind of solution. Okay, sorry, my throat's hurting. When c is equal to 1, you have the regular exponential function. Okay? And by the way, all exponential functions go through the point 0, 1. Okay? When c is equal to minus 1, however, I shouldn't say all, because then that would be going through minus 1. Because when c is minus 1, e to the 0 is 1, but then multiply it by minus 1, you get a minus 1. So that. Then do different c's. C is equal to 2, 3, 4. And what you have are equations that are flatter here, steeper there, or equations that are not, you just get a bunch of them. Now, they all go through, I'm sorry. They don't all go through, sorry. Let me take some of those off. Okay. When c is equal to 3, say, x sub 0, yeah, that would be at 3. So you see, I'm sorry, when c would be 1/2, you would have a function that does like this. It's equal to 2, you would have, one that does like this. 3 would be like this. I mean, they flatten out more here and then go up more sharply. I'm not drawing these very well. And then for minus 1/2, it would be one that goes like this. For minus 2, it would be like this. For minus 3, it would be like this. And they go off. Okay, I'm sorry. These should all coalesce down here. Okay, and this should too. Everything approaches 0 there. Okay. You can't tell whether they cross or not. They really don't, but they do coalesce there. You have a huge family of solutions. Huge family of solutions. Okay? Infinite number of solutions. Okay? Now, what if they gave you an initial condition? Let's say, and you only need one because this is a first order differential equation. So if you have y at some value, and initial condition is sometimes 0, okay? Not always, but it could be. And they tell you this is 3, guess what? This is 1, 2, 3, there you are right there. That's the only one of these curves that's going to be 3 when x is equal to 0. So, get rid of all these other, oops, it didn't erase. Get rid of all these. you're not going to use any of them. Any of those. Okay, I got rid of the wrong one. Nothing here. Even that one is 0. I can't get rid of it. I'd lose the axis too. And basically, this is the one. Okay? There is the one and only of those curves that goes through 0, 3. The only one. Okay? Now, what if you had a different initial condition? Say your x0 is 1. Okay? So y of 1 is equal to negative 2. Well, obviously, this one's out of the question because that's never negative 2. So when x is equal to 1, your y is equal to negative 2 down here. Okay? Well, you pick the curve that goes through that one. There you have it. One and only one function goes through that. Now, I don't have it going down steeply enough. It's going down pretty rapidly there. Okay, so depending on your initial condition, you pick the curve that fits that situation. Okay? Now, those are done by the curves. Let's actually do the work here. First one here, this is the solution you came up with, and you want y is equal to c e to the x. So you plug in a 0 for x, and you get y is equal to c e to the 0. Because when x equals 0, y is equal to 3. This y is now 3. Well, e to the 0 is 1, so c is equal to 3. So your solution here for this initial condition is y is equal to 3 e to the x. That's it. That's the only one it will be. There's no longer a parameter. There is a value because you had that initial condition. Let's do the same down here. We see that negative 2 is equal to c e to the 1. Okay? So therefore c is equal to negative 2 divided by e to the first power. Well, figure out what that is. I think they just probably c is equal to negative 2 e to the minus 1. Okay? So you plug that in, okay, into this. So y is equal to negative 2 over e to the x. Well, you can clean that up a little bit. That would be minus 2. This is e to the 1 down here, so x minus e to the x minus 1. Okay? And that's how they get the answer. They have negative 2 e to the x minus 1. That's probably the cleanest way to write that solution. Okay? And it has no more arbitrary parameters. And it has only one curve that is going to satisfy them. That is the curve for that equation. Okay. All right. My throat is hurting so badly, I need to go get a swig of water. So I'm going to put this on pause. All right, sorry I'm back. Well, I'm back. Sorry that I had to leave. Yesterday my throat started hurting as I talked. Of course, I talked from 8 o'clock in the morning until 9 o'clock last evening. Actually, the second lab finished a little early, so I wasn't talking that whole time. But my throat was hurting the latter part of the day. So I thought to myself, well, tomorrow I'm going to have a cough drop. Well, I went home, hurt a little last night, but not bad. Woke up this morning, felt perfectly fine. So I didn't think any more about the cough drop until I've been in here talking, and now my throat's hurting again. So I wish I had remembered to get a cough drop, but I haven't. Or a throat lozenge, something to lubricate my throat. All right, that was example 1. Let's move on to example 2. Now this is referring to a problem in an exercise set you haven't done yet. Problem 6 up in exercise 2.2 You will be asked to show that a one-parameter family of solutions of the first-order differential equation, here's the differential equation, y prime plus 2xy squared is equal to 0. Okay? You'll be asked to show that a one-parameter family of solutions for that equation is this. Y is equal to 1 over x squared plus c. Okay? Now, sort of hate to do this, but this is basically what you're going to be tested on when you have a test on this, so I think you ought to get used to doing it. Let's actually do the verify this. Take the first derivative of that, and boy, this is going to be a division rule, quotient rule. Okay? If it weren't for that plus c, it would be a lot better off, but it's sort of messing with things. So what we have is, I don't know if you remember your quotient rule. I used to just remember it as what I thought was a straightforward way. Then I was tutoring. I don't know if it had any difference that he came from India or not, but an Indian guy and friend of our family. And he used this rule. Of course, he speaks really fast. But then I've heard Anglo students, American students use this too, saying low D high minus high D low over low low. Okay? Now, what they mean by that, the derivative low times, the denominator low times the derivative of the numerator, that's your high, minus your high, your numerator, times the derivative of the denominator, that's D low, over low low, okay, the denominator squared. So let's do it and see what we get. Low D high, well, low is x squared plus c times derivative of 1. Derivative of 1 is 0. That goes away. Minus high, so that's minus 1. D low, derivative of the denominator is 2x. Derivative of c is 0. Okay? Over low low, which would be x squared plus c squared. Okay? Which is messy, but okay. Alright? Now, another thing we've got to do before we can plug this back in is do y squared. So y squared, because we're going to have to plug that in here, be 1 over x squared plus c squared. Okay? So let's plug and chug and see what happens. Minus 2x, the y prime here, over x squared plus c squared, plus 2x times y squared. Well, y squared is 1 over x squared plus c squared. Sure enough, that is identically equal to 0. So yeah, we verified that is a solution. Okay? Now, they didn't ask us to, but we did. And where is that a solution? I believe it's a solution for all real numbers x, negative infinity, positive infinity. Because since the denominator is x squared plus c, well, wait. I'd say x can't be 0 if c is 0, so I guess we would have to exclude that. So either you don't let c equal 0, or if c is equal to 0, x can't be 0, or something. But, let's hold off on what that interval is. But I think for any positive x or any negative x, as long as your c isn't exactly the opposite of that, the negative of that thing squared, you'll be okay. So, we're not even getting into that. Okay. Now, if we impose the initial condition y of 0 is equal to negative 1. So here's our initial condition, y of 0 is equal to -1. Okay? Well, here's your y. So let's do, and that's a y of x, by the way. So what we have is -1 is equal to 1 over x is 0, that would just be c. So that would produce c is equal to -1. Multiply both sides by c, divide both sides by -1, and you get c is equal to -1. Okay. So our solution then would be, if c is -1, for that, your one and only solution, not a family of solutions, would be y is equal to 1 over x squared minus 1. All right? But, okay, you have some limitations here. It's the same as 1 over x plus 1 times x minus 1. So obviously, x cannot equal plus or minus 1. So you have limitations there. X can equal 0, no sweat there. So this would only be good on the interval from -1 to 1. Because that's the only interval that contains 0 over which this is defined. So your I here, that's the maximum it could be. It can't be -1, that would put a 0 in your denominator. It can't be +1, that would put a 0 in the denominator. It must have 0 in it, so you have to be between -1 and 1. Even though this is defined for x is less than -1, 0 is not in that interval either. Okay. So, it says, considered as a function, the domain here is a set of all real numbers x for which y of x is defined. That's a set of all real numbers except x equals +1 and -1. But considered as a solution for the differential equation, the interval I could be taken to be any interval over which x of y of x is defined and differentiable. As you can see, that would be from -infinity to -1, from -1 to 1, or from 1 to positive infinity. Those are the three places where it could be defined, but you have to consider the one where your initial condition came from, x equals 0, that's only present in that middle, -1 to 1. Okay, that's the only place you can define that. Now they went on and drew this solution, this thing right here, and that's the rational function. You have a vertical asymptote at -1, and you have a vertical asymptote at 1. And they told you or showed you it goes like this here, like this here, and like this here. Okay? Because the y-intercept here will be when x equals 0, y is equal to -1, so that's why it's down here. This is the only part of this that does not contain, when I say this, can't contain either -1 or 1, so anything from here to here, that's the part where the function is defined and it contains the initial point x equals 0. These over here, the function is defined, but it does not contain your initial point, so you can't use those. Now, I'm not absolutely convinced. In fact, no, they're right. Okay. I was going to say I'm not convinced that the y equal 0 is your horizontal asymptote. Then you plug it in, and yes, it is. That is your horizontal asymptote. So there are no values for x where your y will be between -1 and 0. Okay, surprising, but it's true. All right, let's go to a second order initial value problem. Example 3. Now this is going back to example 9 in section 1.1, which you hopefully maybe have done by now, but if not, hopefully you will do it. It said we saw that, though we haven't seen it, you may have. I have it. X is equal to C1 cosine 4t, I think we've seen this problem before though, plus C2 sine 4t. This is maybe the first one we did today. Two parameter family of solutions for this second order differential equation. X double prime is equal to, plus (16x) equals 0. Now your x is your dependent variable now, t is your independent variable. So obviously what we've got to do here is do x prime is equal to, just like we did before, minus 4c1 sine 4t, because the derivative of cosine is sine is negative sine, and then chain rule gives you the minus 4, and then you get a plus 4c2 cosine 4t. When you take the derivative of that, x double prime is equal to minus 16 c1 cosine 4t, because derivative of sine is cosine. The chain rule gives you another 4 out there. Minus, because derivative of cosine is minus sine, 16, because the 4 that's there and a 4 from the chain rule, c2 sine 4t, derivative of cosine minus sine 4t. Okay? And then you plug that in here. Your x double prime is minus 16 c1 cosine 4t minus 16 c2 sine 4t. Okay, that's your x double prime, plus 16 times c1 cosine 4t plus c2 sine 4t is equal to 0. When you plug in that value x into this x here into that x there. And then I think it's pretty obvious that minus 16 c1 cosine 4t minus 16 c2 sine 4t plus 16 c1 cosine 4t plus 16 c2 sine 4t is identically 0, because this one and this one add to 0, this one and this one add to 0, 0 is equal to 0. Yes, that is a solution. That's your two-parameter solution for this second order ordinary differential equation. Okay? If you're going to make it an initial value problem, you need not one, but two initial conditions. Okay? And you pick a t, or they give you a t. Okay? And here's the initial condition. X at pi halves. Now that doesn't feel like initial, but it's some fixed point. They tell you that's equal to negative 2. And similarly, x prime at that same point, pi halves, is equal to 1. Okay? Man, my throat's hurting again. So, let's plug and chug. We've got our solutions right here, and we're going to plug in these in turn. Okay? Here's your solution. Let's plug it in. And this x is going to be negative 2 is equal to C1 cosine of 4 times pi halves plus C2 times sine of 4 times pi halves. Okay, put extra parentheses on sine but not on cosine, doesn't matter. It doesn't matter. Okay, so let's see what we got. Minus 2 is equal to, what is cosine of, well, 4 times pi halves would be 2 pi. What is cosine of 2 pi? Same as cosine of 0, 1. So this would be C1. What is sine of 2 pi? That's 0. So we lose the C2. We don't have any way to determine it. So C1 is equal to negative 2. Well, the second initial condition is this one. So we go up here to our x prime, and we know that's going to be 1 when we plug in pi halves for this equation. So that's going to be 1 is equal to minus 4, and we already know C1 is negative 2, so let's just put that in. Negative 2. That's your C1, negative 2, times the, if I can read it, I think that's sine of, since we've already done this, 4 times pi halves would be 2 pi. Okay, plus 4, we don't know C2, so we're going to leave that alone now, times cosine of 2 pi. Okay, all right. Well, again, sine of 2 pi is 0. Okay, so we have 1 is equal to, this goes to 0, and this would be 4C2, and cosine of 2 pi is 1, 4C2. So this indicates that C2 is equal to 1 over 4. Okay, now we've got our two constants that meet this initial condition. No longer arbitrary, they are fixed here. So go back to our original thing, and our general solution is x is equal to negative 2 cosine 4t plus 1/4 sine of 4t. That's it. There is your one and only one solution that fits this ordinary differential equation, second order ordinary differential equation, at the point t equal pi halves, okay, under those initial conditions. So let's see what we got. Negative 2 cosine 4t plus 1/4 sine 4t. That is your one and only solution for your initial equation, this one, with these boundary conditions. Okay. Now, they bring up something that's occasionally brought up in calculus classes, and they are important issues to think about, but they are the two sort of paired conditions of existence and uniqueness. Two fundamental questions arise in considering an initial value problem. Does a solution of the problem exist? And if an animal, goodness gracious, if a solution exists, is it a unique solution? Okay. Head stopping up again. So it's not just a sore throat now, it's trouble breathing. I hate to do this again because it seems like I should last another 10-15 minutes. But I really want to go drink something other than water that'll maybe loosen my head a little too, like a Coke or something like that. I know you were thinking brandy, but I don't do that, so anyway. So let's look at these. For the first order initial value problem, and this was number 2 that we did before, where not this one, but the one we did before that. We ask, does the differential equation dy dx equal f of xy possess solutions? Okay? Do any of the solution curves pass through the point x0, y0? Both of those must be true for the solution to exist. Okay, so that's the existence part of it. Uniqueness, when can we be certain that there is precisely one solution curve that passes through that point? Okay, now example 1, was looking at 2 first order initial value problems, 2 different initial values. The phrase a solution is used rather than the solution of the problem. The indefinite article a is used deliberately to suggest the possibility other solutions may exist. At this point, it has not been demonstrated that there is a single solution of each problem. So the next example will illustrate an initial value problem with 2 solutions. Let's see if we can get this one done. And this probably is going to come close to being as much as we can get done today. Let's see. Might be able to get a little more, but let's see. We did earlier today. Okay. They say each of these solutions, y is equal to 0, and y is equal to, you should recognize this, 1 over 16 x to the 4th. Okay? Both of those functions satisfies this differential equation, dy dx is equal to xy to the 1/2. Word, my throat hurts. Okay. We've already shown that. Okay. But now we're given an initial condition. Y of 0 is equal to 0. Well, guess what, team? The first one there, obviously that's true. Y is equal to 0, solution everywhere, including at 0. And when you plug in x equals 0, the second one is also 0. So, both of those solutions, those functions, satisfies both the differential equation and the initial condition. So, existence is not an issue. It really does exist. The answer exists, but uniqueness is not met because you have 2 completely different functions that both solve that equation. Okay? And if you go back and think, I drew the blue curve of that earlier, and I suggested that the x-axis was the curve beneath it, but I didn't. We didn't have any real reason to be plugging those in, but here we do. So with this within the safe confines of a formal course in differential equation, one can feel fairly confident most differential equations will have solutions, and that solutions of initial value problems will probably be unique. Not always the case. Real life, however, is not so idyllic. Therefore, it's desirable to know in advance of trying to solve an initial value problem whether the solution exists, and when it does, whether it's the only solution of the problem, existence and uniqueness. Since we're going to consider first order differential equations in the next two chapters, we consider here without proof a straightforward theorem of a solution of a first order differential equation with a how to say this, they say we'll wait till chapter 4 to address the questions of uniqueness and existence and uniqueness in second order initial value problem. So here's the first theorem, and since I'm not sure all of you have books, goodness, my throat's hurting like crazy, and I can't breathe, so it's double whammy. Theorem 1.2.1, existence of a unique solution. Let R be a rectangular region. Almost sounds like Cal 3, doesn't it? A rectangular region, okay, in the XY plane, okay, defined by A is less than or equal to X is less than or equal to B, and C is less than or equal to Y is less than or equal to D. Okay. Now this region also contains the point X0, Y0. In other words, your initial value. Somewhere in the interior. Okay? Okay. In other words, X0 can't be A or B. It can't be a boundary. And the Y0 can't be C or D. It can't be a boundary. X0, Y0 must be, in other words, A is less than X0 is less than B, and C is less than Y0 is less than D. Can't be equal to. It has to be X0 in between A and B, and neither one of them. And C and Y0 has to be in between C and D, but neither one of them. Okay. So there's the given, or the first part of the given. Next part. If f of xy and, now here they're introducing a partial derivative, partial of x with respect to y. Goodness gracious. Goodness, my throat hurts. If both of these are continuous, both the function and the first partial with respect to y are continuous on that same region R, okay, then there exists some interval I0 okay, such that x0 minus h to x0 plus h with h greater than 0 contained in that closed interval a to b. All right. Now, this kind of reinforces what I was saying before, but actually makes it a little stronger. For some value h, and h can be very, very small, but it can't be 0. and it has to always be slightly positive, or positive in some nature. Can't be negative or 0, greater than 0, okay? And you go the h to the left of x0 and the h to the right of x0, you still have to be in this thing. So we said x0 can't be on the boundary. It can't be super close to the boundary either. You've got to always be able to get an h into the left and or into the right. Okay? Past that. Okay. Okay? And a unique solution, okay, a unique function, okay, y of x, defined on I0, okay, that is a solution of the initial value problem. Okay. And that's the problem that we saw back on page 15, first order differential equation. Okay. Geometric interpretation. Okay. That place. Now, this is one big, wordy, actually 2 sentences, but the second sentence has so many pauses and commas in it that I have to stop and go back and read that again. Okay. The first sentence says, if R is a rectangular region in the XY plane such that your X is between A and B, Y is between C and D, contains a point X0, Y0 in the interior of that range. Okay, we said that. Okay. Let R be that. Okay. Now, if f of xy and its derivatives are continuous in that range R, that implies there exists some interval there exists some interval I0 h units from x 0 where h is positive, contained in AB, and a unique function y defined on AB that is a solution for the initial value problem. So this is basically telling you you do have a unique solution and the solution exists. The first line basically says it exists, kind of, and the second says it's unique. Okay. I didn't think we would take that long, but it did. All right, we did run out of time. I can find my pencil here. We will start next time with example 5, top of page 18. And we almost finished 1.2. So I think you can do problem 1, either 3 or 5, either 7 or 9, either 11 or 13, or both on all these. Try 15. And I would say let's hold off. Let's stop at 15 and we'll try to pick up the rest of those after we do that last page or so, that last example. Okay. All right, good deal. Sorry no one showed up today. Sorry I had to take a break or two, and it's been pretty rugged. Y'all have been perfect attendance up until today. Both of you have been here every day, but today, neither of you. Who is? Hope to see you on Thursday. We'll close this out.